You are given two sorted arrays of distinct integers. Pick one array and walk from left to right. Whenever both arrays contain the same value, you may switch to the other array at that meeting point. Add up every value you visit once. Find the maximum possible score, and return it modulo 1,000,007. Example 1, nums1 is 2, 4, 5, 8, 10 and nums2 is 4, 6, 8, 9. The shared values are 4 and 8, those are the only places a path may switch. One best route collects 2, then 4, 6, 8, and 10 for a total of 30. Example 2, nums1 is 1, 3, 5, 7, 9 and nums2 is 3, 5, 100. The shared values are 3 and 5, those are the only places a path may switch. One best route collects 1, 3, 5, and 100 for a total of 109. When you hit an intersection, it is tempting to peek all the way to the end of both paths and guess which lane switch yields the highest score. But simulating every combination of lane changes creates an exponential explosion of choices that will cause a brute force solution to time out. The breakthrough: intersections are mandatory bottlenecks. Every path must pass through those exact values. That splits the highway into independent stages between toll booths. Focus on segment B, trapped between toll booths 4 and 8. Choices inside this stretch never affect the future, so pick the better lane locally. 6 beats 5 here, and we greedily lock in the bottom lane. To compare stage by stage in one pass, run a synchronized race with 2 pointers. Whichever pointer sees the smaller value steps forward and collects those points. Here 2 is less than 4, P1 advances and sum1 becomes 2. Now both pointers meet at toll booth 4. When both pointers collide at a toll booth, a segment ends. We look at the running totals from that stretch, harvest the maximum into our global vault, add the booth value, and reset the segment counters to 0 for the next stretch. When one lane runs out of road, let the remaining lane finish its final stretch. Compare the trailing tail sums one last time, add the winner to the vault, and cross the finish line with the guaranteed maximum score. We set up our environment. Pointers I and J track our current position on each highway, while sum1 and sum2 act as local meters to accumulate score segments between intersections. Inside our loop, if the top lane's value is smaller than the bottom lane's value, the top lane has catching up to do. We harvest its current number into sum1 and advance pointer I forward. Conversely, if the bottom lane's value is the smaller one, it must step forward to catch up. We add its number to our sum2 meter and advance pointer j to the next card. When both pointers collide at an identical number, we've hit a toll booth. We greedily select the larger sum accumulated from this segment, add the intersection value to total score, reset our local meters to 0, and advance both pointers past the gate. If one highway finishes early, the other lane might still have tarmac left to run. These cleanup loops let any remaining trailing values sweep forward, gathering the final stretch of points into their meters. Finally, we take one last comparison of the trailing tails, add the winner to our grand total, apply our modulo for safety, and cross the finish line with our maximum possible score. Let n be the length of nums1 and m the length of nums2. Time is big O of n plus m, each index advances at most once across the merge and cleanup loops. Space is big O of 1, only pointers I and j plus 3 running counters are stored. Function max score takes the two sorted arrays nums1 and nums2. Set pointer I to 0. Set pointer j to 0. Set segment sum1 to 0. Set segment sum2 to 0. Set the global total to 0. While both pointers are still inside their arrays, compare the current values. If the top value is smaller than the bottom value, then add nums1 at I into sum1. Advance I by 1. Else if the bottom value is smaller, then add nums2 at j into sum2. Advance j by 1. Else the values match at a shared toll booth. Add max of sum1 and sum2 plus the booth value into total. Reset sum1 to 0. Reset sum2 to 0. Advance I by 1. Advance j by 1. While nums1 still has elements left. Add nums1 at I into sum1. Advance I by 1. While nums2 still has elements left. Add nums2 at j into sum2. Advance j by 1. Add the final max of sum1 and sum2 into total. Return total modulo 1,000,000,007.